A little old for dolls, aren't we?
This is not a doll. This is a demonstration model for the next story we gotta do, which comes right from the fan site.
Okay, tell me more.
I'm a skydiver, right? And I'm falling through the air. And my parachute has utterly failed. Looking desperately down at the ground for something to break my fall, I spy a children's playground and a seesaw with a little girl at the other end. Not worrying about her, I aim for this end of the seesaw, go straight upright. At the last second, I hit the seesaw and catapult that poor little girl up to the top of the 7-story building, where amazingly she lands safely.
Wow. Sounds almost too good to be true.
I thought the same thing.
Attached to your missiles.
Our little girl over here is supposed to be an average 6-year-old, and so we've made her weigh 50 pounds. Now, if the physics in this story are correct, the water barrels, when they hit this end of the seesaw, are going to launch her straight up about 70 feet or 7 stories.
I've calculated that filling the barrels with 1,150 pounds of water and then dropping them from 75 feet should exactly match the skydiver's free-fall impact force of 85,000 foot-pounds. So I'm going to pull the safety, but you know what? I don't want to be anywhere on this lot when we drop this thing.
And that actual mayhem is now just moments away.
All right, here we go. Skydiver seesaw in 3, 2, 1.
Darn, the seesaw broke. It just kind of like folded in half.
The bench is buckled, but the full extent of this disaster is best assessed from ground level.
It not only crushed it right at the pivot point, but it also crushed it right at the end here. So, you know, that's a heck of a lot of force.
A lot more than we considered. We're going to have to rethink this thing.
Yeah, even if this was a solid bar of steel, I don't think it would have taken it.
Yeah. I can't help but feel this nagging feeling in my head that there's a big difference between 1,000 pounds of water in steel cans and a soft 100 and some odd pound skydiver falling at terminal velocity.
Now we need to figure out, if we're going to make this work, how to get all of that energy over there to come over here to the little girl without wasting itself on breaking things in the process.
In short, the fact that a home-built seesaw cracked under the weight of 3 sharp-edged barrels doesn't prove or disprove the myth. Jamie's decided to build his bench in 2 parts, both hinged on a pivot.
Where's that put us as far as our yield strength?
The big picture here is to maximize the energy transfer from the falling man to the girl and to keep the seesaw intact.
So I started thinking about, what do I know that is really massively strong and lightweight? And so what I came up with was a construction crane like this toy here. Instead of relying on something to not bend, they put a cable across the top of it, so the load that's being experienced is on that cable. And instead of a bending force on this spar structure here, you've got a compressive load. It's hard to see here, but the load is this way. And so you end up with something that's able to build whole buildings, and yet there's really not a whole lot there.
While Jamie thinks big, Adam goes small scale to get some idea of what to look for when they try this again at full force.
Building a toy teeter-totter is easy peasy, and I don't know, kind of wholesome, you know? This is our little girl, as creepy as she looks, and this is our skydiver, as much as it looks like a round ball. They are the equivalent weight relationship of our real skydiver and our real girl, about 3.5 to 1. What I want to investigate with this is what happens to her when the skydiver hits the seesaw. The seesaw doesn't break. Where does she go? What is her trajectory, and what can I predict about her trajectory?
So Adam starts test number 1 from 10 feet up on the scissor lift. A plumb line indicates the perfect drop point, and it's bombs away.
3, 2, 1. Oh God, that's one of the best high-speed shots ever. I dropped the weight from about 10 feet up, and she smacked into that lamp at a pretty high speed, which means
She's going higher in the air than the lead weight is starting from. That tells me there might really be something to this.
The best Mythbusters tradition. The fast-setting winter sun means this next attempt is absolutely our last one. It's now or never. Let's go up.
They can only cross their fingers and hope that this time the girl misses the guide wire.
Here we go! 3, 2, 1!
Well, Jamie said it would work. The Skydiver Simulate did hit 122 miles per hour. And despite the colossal sideways arc, little Ariel flew way higher than anyone dared to hope.
She flies about level with our spreader bar, and that's 130 feet.
That's 13 stories, and that was with an angle like this. If we got her to go straight up, she would have cleared 200 easy.
This myth sounded totally improbable from the get-go, but Jamie and Adam kept the faith.
The fact is, normally when we're testing myths that have to do with broad guesses about physics, they're usually grossly overestimating what's possible. And in this case, we've come across a myth where the physics are grossly underestimated.
If you had an impossibly strong seesaw, if you had a parachutist that didn't just go splat when he hit it, you'd be capable of launching a little girl up at least 13 stories in the air.
So, how do we call it? Well, sad to say, it's busted. Jamie built the best possible seesaw and almost doubled the 7-story flight. But that little girl would be just as dead as the Skydiver.